I repeat that I'm working in CINECA as an open form expert and visualization engineer. So today I changed my topic. So from In-Situ I moved to GPU porting by using third-party libraries, in particular PETSc. And in this presentation we talk about the open form case. So in the previous presentation I see a lot of codes in many scientific areas that have been ported to GPUs. In this presentation, we refer only to open form and the work we done until now for the hexaphone project that will start in a few months. So the presentation is mainly divided in 6 parts. So we start with the motivation of this work. We present the basic features of two libraries, PETSc and PETSc Perform. We see how to use the library we developed in PETSc Perform, some results, intranode results on our workstation hosted in KAUST and on one node of Marconiloo 100, and the conclusions and the future works we will probably do at the beginning of hexaphone. So let's start with the motivation so the starting point is open form. We know that, or probably all of us know this open form is an open source finite volume CFD code, which is the development of open form started during the 80s, so it's pretty old. And he did a good job up to now within a homogeneous hardware ecosystem. It was developed when the machine was mainly homogeneous. So now we are facing the problems of that these application toolboxes have to provide solution with performance portability across different architectures. So not only homogeneous, but different. For example, the main are NVIDIA GPUs with CUDA, AMD with HIP, and Intel GPU with one API. These are the main 3 architecture we will face in the near future. And so in this day, for example, in CINECA we have Marconiloo 100, which is a Power 9, which has a Power 9 architecture plus NVIDIA Volta 100. But as in presentation of the presentation, we see that Leonardo, the same machine, we will have Intel plus NVIDIA. So this is the current and the next architecture of the current and the next generations of HPC. So a few words about PETSc. PETSc is a portable, as the acronym is, the portable extensible toolkit for scientific computation. It's a very well-known library developed in the 90s and has inside many linear, nonlinear, and time-dependent solvers. He has support for many language like CUDA. So under CUDA there is CUDA, CUDA+, NKL for Intel, OpenCL. It has interfaces with a lot of many third-party libraries. So third-party of PETSc, which is another third-party normally for a safety code. One of the most probably third parties Hyper. He is still actively developed. We have around 20 developers around the world that are actively committed in PETSc, and recently they had some grant for support versus AMD GPUs and Intel. The idea that started 1 year ago is to couple PETSc with OpenFOAM. So we decided to develop an interface, sort of adapter, like we normally do in situ visualization. Here we are developing an adapter for linear algebra in order to offload the linear algebra part to the backend, which is in this case PETSc. After 4 or 5 months of development with co-development with particular Mark Olesen from ESI, we released a module which is named External Solver, which is now public, with the following features. So accelerate the linear solver part of the simulation, as I told before. So to offload to the PETSc backend. Easy to use PETSc inside OpenFOAM using dictionary. So for one that knows OpenFOAM dictionary is the native language to customize simulations in OpenFOAM, and also to provide access to the third-party libraries of PETSc. For example, the direct solvers like MAMS or SuperLU, or the multigrid inside like iPrep or NL. And since we are talking about GPUs, the idea is to provide an interface also to AMGX, which is developed by NVIDIA. So up to now, there is no official porting of AMGX into PETSc. So what we have done up to now is to interface OpenFOAM directly to AMGX. We are planning to make the porting of AMGX into PETSc in order to be called from OpenFOAM using PETSc for FOAM like we normally do for iPrep. So a few words about the mathematics behind PETSc for FOAM. All you know that OpenFOAM solves assemble a sparse linear system, and this sparse linear system is solved by native built-in solver. So the idea in PETSc for FOAM is to offload this linear solution to PETSc. So a.x equal to b is solved by one of the iterative linear solver that is present in PETSc. As you know, this sparse linear system is if conditioned, so we need to precondition the solution. So we need to multiply the system by a non-singular matrix M, where M is the preconditioner. A is the matrix that is assembled by OpenFOAM and is stored in memory in the LDU format. So it's mainly divided in 3 parts: the lower part, upper part, and diagonal part. This matrix is offloaded to PETSc and converted into the native format of PETSc, which is CSR. Once this conversion is done, the matrix M is constructed. So it's not converted, but it's constructed from PETSc directly. So since the matrix is converted, we have a doubling of memory. So we have A in memory in the LD format and A in memory in CSR form. Regarding the solution X in the right-hand side B, these are only, in PETSc, only shallow pointers. So it means that there is no mem copy. What about the residual norms? The default convergence PETSc is the L2 norm. So we can use absolute or residual or relative tolerance, but convergence is based on the L2 norm. OpenFOAM uses a particular norm, which is not implemented in PETSc, which is a L1 scaled norm. It's a very particular norm which I didn't find in any other code, and this I renamed scale because the L1 norm is divided by, which is called norm factor, which I reported here, the definition which you find in the OpenFOAM code. This is scale because if the solution X is 0, the residual is 1. So the default algorithm we implemented in PETSc for form for making this conversion from LDU to CSR, which is the first one we implemented at the beginning, is a traversal-based algorithm based on the math set values approach. I decided to put this name, math set values approach, means since it is based on the math set value API in PETSc. I reported here the pseudo algorithm. This algorithm is divided in three parts. One is the loop over the lower part of the matrix. Another one is the loop over the diagonal part, and at the end is the loop over the upper part. For each value or a bunch of these values, we call math set value. In the upper part, we can make this loop row by row, so it's we can increase the performances of this loop. But the main feature is that you have to call this function for each value, and this is not probably the best way to do it in terms of performance, but it's general. It's general because the default target matrix is CSR, but in principle one can choose the best target matrix that the user wants. For example, if one is working on an Intel machine, can use the optimized format, which is math MPIJ MKL, for example. If one want to use Hyper, can use the math Hyper format, or another one is the math cell that has some optimizations for KNL. Performances are linear in log-log plot. I report here the performances of three different math types. The default one is MPIJ, the optimized for Intel MPIJ MKL, and the symmetric format, which is math MPI SBIJ. As you see, the red plot is above the blue one, since because the matrix, since it's symmetric, you need to convert half of the values. So it's faster to be converted. So can we do better with respect to this general approach of calling math set values for each value of the LDU matrix? Stefano Zampini by PETSc proposed a new approach, which is implemented, I think, in a dev version of PETSc, which he proposed to make an intermediate step from LDU to the final target, which is the CoO. This conversion from LDU to CoO is done on CPU and is general. So when PETSc has this CoO format, can decide to convert to the final target, which can be a format compatible for GPU. A developer of NVIDIA, Matthew Martinez, proposed a different approach, which is now moved into PETSc Perform, which runs completely on GPU with respect to the first approach. And this algorithm proposed to offload the LDU arrays onto device and performs there a radic sort and store this permutation on the memory of the GPU for the subsequent time steps. So when this permutation is calculated and stored, you need to pass for the subsequent time steps only the values and not the structures of the matrix. And using this permutation, the matrix is converted very, very fast. Everything is written in CUDA. It works both in CUDA 11 and CUDA 10. The interface of PETSc Perform is very, very simple. You need to make mainly two changes. One is to add the name of the library into the contradict, so you need to add a line with written leaves PETSc Perform. And the other one is to make changes in the FB solution dictionary that is present in a typical simulation, typical case. So you need to change the name of solver into PETSc. Preconditionally, you can also write preconditional PETSc, but it's not mandatory. Then you add a subdictionary which is PETSc, and then another subdictionary options, and there you add all the command line flags you normally use for a PETSc simulation. For example, here I want to use a conjugate gradient solver, so I put KSP underscore type CG. I want to use an algebraic multigrid as a preconditioner, so I put PC underscore type GNG. And as matrix type, I want to use the QSparse formats provided by the QSparse library. Regarding tolerance, relative tolerance, and max number of iterations, these are the same as before. They are changed. In principle, you can decide to use PETSc for only a single variable, so not all of the variables that are solved in OpenFOAM. So remember that OpenFOAM is segregated, so each equation is solved by a linear system. One can decide to solve, for example, only the pressure with IPRE and still use the Gauss-Seidel, or its name smooth solver in OpenFOAM, to use Gauss-Seidel for the three components of the velocity, or use for all the equations dedicated PETSc solver. For the moment, we have make debugging test to see how it's working using this the solvers that are inside PETSc. So we tested on a node of a Marconi 100 with is equipped with power 9 CPUs and 4 Volta 100, and on a small development box, KAUST, which is an Intel machine plus 2 volt at 100. We use as a benchmark the lead-driven cavity flow, which is described by, I don't know if Ivan already told of the lead-driven cavity, but is a very famous benchmark that you find also in the tutorial of OpenFOAM. It's a very simple physics. It's a laminar flow into a box, and we run IcoFOAM for 20 time step with 2 pressure corrections with 8 million cells, which fits into one GPU. We use PETSc version 3.14, CUDA 10, and for the timings we use the log flag. For these preliminary results, we compare the geometric algebraic multitude native provided by FOAM against the smoothed aggregation version provided by PETSc, using different smoother. For example, in this slide I reported the customization of the smoothed aggregation with the Chebyshev smoother. And already said we're using log view for the timings. So here some results in the Skylake workstation. We have 5 histograms with different matrix obtained with different matrix types. The first one is only on CPU using the native multigrid. The second one is the multigrid provided by PETSc that run completely on CPUs. The third one is the same solver of the second case, but we're using the QSparse matrix format. Fourth case, we use the Cocos matrix format, and the third case is the Vienna CL format, and the last one is the QSparse. So as you see, the scalability is good for both regarding the pure CPU implementation, both for native and PETSc. Okay. Regarding the GPU implementation, you see that we have a minimum with 16 processes, but the time reach sort of plateau at 8 processes. Also, the performances of also look at the performances of the preconditioner. Now is the orange part of the histogram. The preconditioner in PETSc is done completely on CPU. So only the yellow parts of the Krylov solver is run on GPU. This is why you see this reduction in the yellow part moving from the CPU implementation to the GPU ones. Also, you see that Cocos and QSparse runs very fast when you have a number of GPU that is the same as the number of processes. Right? You look at the yellow part with 1 and 2 processes is very small. Also, the minimum is when the number of processes is 2, and then this yellow part starts to increase. While the CPU construction of the precondition, so the orange part, continue to decrease from 1 to 16. The result is that the minimum is around 8 processes. Here I reported some numbers. So the overhead in the matrix conversion from LVU to the final target, which is CSR, which is around 25 seconds for 40 assemblies. So 20 times steps multiplied 2 pressure corrections. So the preconditioner is constructed each time on the CPU, which is expensive, around 30 seconds per solve one proc, but it scales very well. CPU only runs slightly faster for PETSc, except for the one processor case. Regarding Krylov solutions, we have 20 iteration multiplied 2 pressure corrections, multiplied 20 time steps. So we have total of 800 total iteration, and it takes around 6 seconds with 1 GPU and 4 seconds with 2 GPU using CoolSparse. And the fastest configuration we found is AIJ Cocos with 16 API processes. We also have to mention that we have around 510 overhead coming from the logging, because all the byte calls become blocking for the logging, due to the logging. In PETSc for Phone, we implemented a new feature, which is we call it caching, to improve the performances. This caching can cache the matrix converted or the preconditioner constructed for the successive time steps. So in this way, for example, we can use the same pressure operator for the 2 pressure corrections. Okay, so we can skip constructions and the conversion for 1 time steps. To activate this caching, we need simply to add into the FU solution a subdictionary named caching, where we specify that we want to periodic update the conversion and the construction of the preconditioner, for example, up with the frequency specified in the dictionary. So, for example, here, the matrix converted after 2 times and the preconditioner after 4 times, 40 times, for example. Want to keep the same precondition for all the simulation. Using this particular setup, where the matrix is converted after 2 times and the precondition is keeping memory for 40 time steps, obviously we have completely different results, because now the orange part is much lower, since the precondition is constructed only 1 time. Also, the conversion is reduced because we have less conversion, and the yellow part starts to be has a major impact. But the minimum is, regarding the GPU solvers, still is with 8 processes. The results of Marconiloo 100 are very similar. The difference now is that the minimum of the GPU part, so the yellow part, is around 4 processes, and not as before, which was 2. The minimum is shifted from 8 to 16 processes, but the main behavior is maintained. So we are at the conclusions. We presented the capabilities of the PETSc Phone. so the mathematics which is behind, motivation that around the development of this library. Obviously, we presented preliminary results of a very simple case like the data cavity, where the main task is the solution of Poisson equation. Obviously, we had to see how it works in complex scenario, and we are facing this. We also have a collaboration between Stefano and Martina from NVIDIA to release a paper on the results we are achieving with using more complex cases, in particular for for bigger case, not like this one, which has only 8 million cells. Also, the speed up of the matrix assembly is an important task that for the moment cannot be easily ported to GPU. We will face this into the Hexagon project. I can mention a parallel activity that we are doing with Federico Broggi from INGV, where we are reducing the execution time in the matrix assembly by using X-precision. Okay, I think that for today it's enough.